The last section of this unit, 5.3, is on geometric sequences. So very much like 5.2 was on a specific type of sequence, so is this one. So we know arithmetic sequences involved adding from one term to the next. Geometric sequences also involve a specific operation to get from one term to the next. So since it's a specific type, it will have its own formula. So all of our objectives today involve becoming familiar with geometric sequences. And the very last objective is one that sometimes people have a hard time wrapping their head around, this idea of an infinite series. But hopefully by the end of those examples, it'll make sense of what we're trying to look at with those. So a geometric sequence, rather than adding by some value to get from one term to the next, with geometric sequences, we are going to multiply to get from one term to the next. And remember last time, the number that we added by was called the common difference. And we said it was the common difference because we could subtract to figure out what they added by. This works almost the same way. The value that you multiply by is called the common ratio. And in formulas, it's going to be represented by R. So for example, if I had this sequence, 8, -2, 1/2, ... First off, it's geometric if I'm multiplying by the same thing each time. Now, if you look at this and you're like, I don't know what they're multiplying by, to see what they're multiplying by, take one number and divide by the number that came before it. If I simplify that, that comes out to -1/4. That is R. That is the common ratio. They are multiplying by a -1/4. If I wanted to double check that, if you took 1/2 and you divided by -2, well, if I really wanted to clean this up, that's like over 1. And remember, we said dividing is the same as timesing by the reciprocal. I still get -1/4. So to figure out what they're multiplying by, take one term and divide by the thing that came before. That's why it's called the common ratio. We are technically setting up a ratio when we do this, something over something. So write the first 6 terms of the geometric sequence with a sub 1 being 6 and r being 1/3. Well, they gave me the first answer. So a sub 2, all I have to do is take 6 and multiply it by r, because they told me they're multiplying by 1/3. 6 times 1/3 would technically be 6/3, or just 2. So then a sub 3, I would take 2 times 1/3, which would be 2/3. A sub 4, I would take 2/3 times 1/3. Remember, for multiplying, you do not need a common denominator, so just multiply straight across. 2/9. A sub 5, I would take my 2/9 times 1/3, and I will get 2/27. And one more, term number 6, I would get 2/27 times 3 is 81. Unless MyMathLab tells you otherwise, I would prefer them to be left in simplified fraction form. All right, look at this guy. Write the first 6 terms of the geometric sequence with a sub 1 being 10, and then it gives me the rule for the sequence. So I have my first answer. So to get a sub 2, Notice where 2 is sitting. It's sitting in place of n, so we're going to plug 2 in for the n. This is a recursive setup, so we always have to use the previous answer to get the next one. If I simplify this, it's actually just negative 3 times a sub 1. Well, what was a sub 1? It was 10. So it turns out my second answer is negative 30. A sub 3, I'm going to plug a 3 in for the n's. So I'm going to use my previous answer of negative 30. And I get 90. So at this point, you might be able to spot the pattern. They went from 10 to negative 30 to 90. What are they multiplying by? They're multiplying by negative 3. So if you want, you can skip the work and just continue multiplying by negative 3. So 90 times negative 3 would be negative 270. Negative 270 times negative 3, positive 810. And 810 times negative 3, negative 2,430. Don't think you've done something wrong if you get some pretty large or pretty small answers today. That will happen when you're multiplying. So now, just like last time, since this is a specific type of sequence, we do have a formula for it. So the general formula, a sub n equals a sub 1 times r raised to the n minus 1 power. And I would keep r in parentheses. That's going to help you avoid mistakes, especially if r is negative. And again, on the test, you do not have to have this memorized. They will be given to you. You just have to know how to use them. So write a formula for the general term, the nth term, of the sequence. Then use the formula to find the 8th term. So if they first want me to write the general term, this is where we're going to keep in terms of n. We're not going to plug in anything for n first. So if I set up my formula, a sub n equals, what's a sub 1? What is the first term? It's 5. Times, now I need to know what r is. I need to know what are they multiplying by. If you're not sure, take one number and divide by the number that came before. Oh, I can see it's negative 1/5. They're multiplying by negative 1/5. So that's r. And I'm not plugging in anything for n. So this is the first thing they wanted. This is the general term. Now, sometimes people ask, wait, can't we multiply 5 times the negative 1/5? Can't we simplify it? My answer is no. Because of that variable exponent up there, I can't actually combine them together. Now they ask me to use it. They say, use the formula for a sub n to find a sub 8, the 8th term of the sequence. So we're going to plug 8 in. For n. And now I want to evaluate this and see what my answer would come out to. So if we do this to the 7th, so what I recommend doing, if it's going to want this answer as a fraction, here's probably the easiest way to do it. For now, let's keep this 5, and let's worry about this fraction. So let's do negative 1 to the 7th. So negative 1 raised to the 7th power. If you do that, that's still negative 1. And then I want you to do 5 to the 7th. 5 to the 7th is a big number. And then the last step is to multiply them together. So I would get negative 5 over this lovely denominator. The last thing, we would simplify it. I believe we can divide 5 into both of those. So I get negative 1 over 15,625. Not a pretty answer whatsoever, but that is term number 8. Now, if they asked for a decimal, well, you could just divide that and do the decimal. Depends on how we want the answer written. Okay, next example. The table shows the population of the U.S. in 2000 and 2010 with estimates given by the Census Bureau for 2001 through 2009. Show that the population is increasing geometrically. If I want to show that it's geometric, I have to show that they are multiplying by the same thing from one term to the next. So probably the easiest way to check this, if I wanted to figure out what they're multiplying by, I'm going to take one term and divide by the thing that came before. So if you do that in the calculator, if you divide those numbers, roughly you should see this decimal out. Now I rounded it, but that's what you should see. Let's check the next set. If I take 286.6 and I divide by the number that came before, what does that give me? Well, it turns out it's also 1.009 with rounding. Let's check one more. If I did 289.3 and I divided by the number that came before, it turns out I get 1.009. So on a problem like this, we just want to show that for a few terms, they are multiplying by the same thing. In this case, R is about 1.009. That's what we're multiplying by each time. That's my common ratio. So part B says, write the general term for the geometric sequence modeling the population of the U.S. in millions, n years after 1999. So if they want the general term, we're going to write our formula, but we're not going to plug anything in for n. So a sub n equals, the first thing in my formula was a sub 1. What's a sub 1? What would be my starting term? It's 281.4. That was my starting population. Times, what's R? Well, we just said what R was. Now, on problems like this, it will tell you how many decimal places to keep. So let's just say it told me to keep 3 decimal places. And then n minus 1. That's it for part B. I don't want to plug anything in for n. So there's my general formula. Now part C, they're going to ask me to use it. Project the U.S. population in millions for the year 2020. Now here's a mistake I will see people do, and I don't want you to write this down. People will do this. They'll go, oh, okay, so 2020 minus 1. That answer that comes out of that is going to be horribly wrong. Because if you look, what did they say n represented? Right up in part B, n was the number of years after 1999. So if you plug 2020 in, you're telling me 2020 years have passed since 1999. That's a big oof. We do not want to do that. So let me erase that. So what would I plug in for n? Well, you have to tell me how many years after 1999 is 2020. So if you subtract them, we find out that 21 years have passed since 1999. And then I still have minus 1 in the formula. So that's what we're finding. We're technically finding a sub 21. So you can enter that all in at once if you want. And let's round to the nearest tenth. So you should get 336.6, and then very important that we put the word million on, because this was in millions. Okay, so some of the powerful things about sequences and series, they can be used, once you have the formula, they can be used to make predictions or projections about populations, which is huge for countries, especially if you're trying to determine, will we have enough resources for such and such a thing? Um, so the ability to project is big. Now, just like what we did last time, we talked about series, and I said, hey, when you see the word series, I want you to think of sigma. We are going to be finding the sum. So we're going to be adding up all of our terms together. So for a geometric series, we do have a specific formula, and it's a sub 1 times the quantity 1 minus r raised to the n, so I keep r in its own little set of parentheses, divided by 1 minus r. It looks super intimidating, but really it's an easy formula to use. We just really got to make sure we simplify it correctly. So let's try it. Find the sum of the first 18 terms of the geometric sequence, and then it gives me the sequence. So what do we all need for this? Well, let's write it down here. These are the 3 items I need in order to use this sum formula. So what's a sub 1? What's my starting term? It's 2. N, how many of them are there going to be? 18 of them. And now I need to know, what is r? What are they multiplying by each time? Well, if you're not sure, take one of the numbers and divide by the number that came before. So that tells me r, they are multiplying by -4 each time. We have everything we need. Let's see if we can get the answer. So the sum of these 18 numbers, 2 times 1. Now, really careful here. This is where people mess up. Keep r in its own parentheses. Raised to the 18 over 1 minus r. So now what people ask me, if we simplify this, they'll go, hey, minus a negative is a positive, right? And I'll go, yes. So that's really just 1 plus 4. And then they'll go up here and they'll say, hey, minus a negative is a positive, right? And I'll go, no. That -4 is affected by the exponent first. So what we would actually have on the bottom, yes, I agree, you could just say 5. But the top, I cannot change that to plus because of that exponent. This is where I would recommend seeing if you can just type this in all at once into your scientific calculator. It should be able to handle this. I would just make sure to put the parentheses in where needed, and you should be able to get the answer. Now, this answer, I will tell you, let me just test it out here on a calculator. Okay, yeah, this is what I thought. Now, here's what my little scientific calculator spit out. This is what my calculator says. What? Another thing that you might see the calculator say, it depends on the calculator, it might also say this. If it says E10, that just means exponent of 10. It literally means this scientific notation. So if I were to actually write this out as a whole number, this is what you would see. I would just move my decimal 10 places to the right. So it's a very large, well, actually very small because it's negative, but it's not uncommon to get some answers that look like that. If you're having trouble entering these into the calculator. This is something you would want to ask me on in the homework help or in class so that we can iron out what the issues are with this problem. Let's look at another one. Find the sum. This time it's in sigma notation. So let's see if we can use this formula again. To get the answer. So what's a sub 1? Well, you might say, oh, it's 1 because that's what's on the bottom. No, I want to plug 1 in to see what my first term is. If we plug 1 in, what would that be? Well, 2 to the first is 2 times 6. It turns out the first term is 12. So now I need to know what are they multiplying by each time. I need to know what r is. Well, I'll let you in a little secret. R, I can tell just by looking at it, r is 2. Well, how do I know that? If you look at that first formula we wrote down today, it looked like this. Whoops, if I can write correctly. It was always r raised to the n minus 1. So r is always going to be the number with the exponent. And now we need to know what n is. How many of them are there? Well, if I'm going from 1 to 10, there's going to be 10 of them. So now let's substitute in. So that's what I want to do. I would quick simplify the bottom. And now you should be able to enter this in all at once. Just use the parentheses where the parentheses are supposed to be. And if you do it correctly, this should be the grand total that you should see out. Again, just put the parentheses in where the parentheses are supposed to be so that the calculator does the order of operations correctly. Okay, the final thing that I want to look at today is that last objective that I mentioned at the beginning, an infinite geometric series. What do I mean by this? Well, for example, if I had something like 1, 2, 4, 8, 16, 32. This is a geometric sequence because I'm multiplying by 2. And what if I asked you, I said, hey, start adding these together now, forever, and tell me what the total is. You might say, wait a second. How do we add something together forever and get an answer? That should not be a thing. It is a thing. And after these examples, hopefully we understand why it is a thing and why it can work. Sometimes it will not work. The formula for this, because believe it or not, there is a formula, the sum of an infinite geometric series, if it goes on forever, you take a sub 1 divided by 1 minus r. So let's try an example of this. I want to show you what I mean by this. If possible, find the sum. So that's important. If possible. Not all of these are going to be possible. So this first one here, 9 plus 3 plus 1 plus ... That's my clue that it's infinite. It's going to keep going. Let's first figure out what are they multiplying by. Let's figure out r. Well, if you're not sure, take one number and divide by the number that came before. And if I simplify it, they are multiplying by 1/3. Now, I forgot to mention on this formula up here, you might want to make this note. This formula, if the absolute value of r, remember the absolute value just turns something positive. So if it was -2, it would become 2. If the absolute value of r is greater than or equal to 1, there is no sum. So what? Well, let's go to our example and I'll tell you what I mean. So if I look at r is 1/3. Is that greater than 1? No. So that means it's possible we're going to get an answer. 1/3 is smaller than 1, so it's going to work. So if I substitute in, what's a sub 1? Well, my first term was 9, over, and then I have 1 minus r is 1/3. If I wanted to combine those, this is like 1/1 technically, so I would need a common denominator of 3. So I would get 2/3. And then remember what I told you, dividing, we're going to times by the reciprocal. So 9 times 3/2. So this is technically over 1. I can just multiply straight across. And I get 27/2, or as a decimal, 13.5. So what does this mean? What did we just find? Well, it turns out that if I kept adding these numbers forever, my total would get closer and closer and closer and closer to 13.5. Why does that make sense? Well, think about it like this. If I wrote, let's actually do 3/10. If I wrote that as a decimal, that's 0.3. So let's say if I started doing this, if I started adding together numbers that were getting smaller and smaller and smaller and smaller, do you agree that my answer, I would just start tacking on more and more decimal places? My answer would start kind of approaching a certain number. That's what's happening here. So it's like as I continue adding numbers on, 9 plus 3 is 12, plus 1 is 13, plus 1/3, my total is going to get closer and closer to a specific number. And in this case, that number it's getting closer and closer to is 13.5. Now, if I was doing something like this, what happens if my answers, instead of getting smaller and smaller, what happens if they get bigger and bigger and bigger each time? Well, if they get bigger and bigger each time, my sum, my total, is not going to approach anything. It's just going to get out of control. So that's why on this formula, the thing that I'm multiplying by, if it's bigger than 1, I'm not going to have a sum, because the thing I'm multiplying by is making my numbers get bigger and bigger and bigger. It only works if what I'm multiplying by is smaller than 1. Let's try another one. So find this sum. I know it's an infinite sum because notice the top, my ending number is infinity. So let's first figure out r, because that'll tell me if it's even possible. So remember, when it's in this form, I told you r is what is being raised to the exponent. So we already know r is 0.2. Is that smaller than 1? Yes. So that means it is possible to find this sum. So what's a sub 1? And you might say, oh, a sub 1 is 4. No, we have to plug that in for n to figure out a sub 1. So if you plug 4 in for n and simplify this, 4 times 0.2 raised to the 4 minus 1. That comes out to 0.032. That's my starting term. I plugged 4 in to figure out what is my starting number. And on the bottom, I have 1 minus 0.2. So I would have 0.032 over 0.8 after subtracting, and then go ahead and divide those, and we get 0.04. Okay, and the last one, let's figure out what r is. What are they multiplying by each time? So if you're not sure, take one of the numbers and divide the number that came before. If you divide those, it comes out to -5. Now, since if I look at my condition, the absolute value of -5 is 5, which is bigger than 1, that means there is no sum. This one, you would either say not possible or no sum. There would not be a total. It's impossible to find the total on this one. All right, and the very last thing here, express 0.7 repeating as a fraction in lowest terms. Now this is crazy. So 0.7 repeating means this: forever. So what ends up happening here, if I wrote this as a sequence, I could think of it as, well, it was 0.7 plus 0.07 plus 0.007 plus, and so on. Because if I start adding these together, I'm going to get my 0.7777, and so on. So what we can actually do, this is weird how this works. If I asked you to tell me what is r, what are they multiplying by on this? Well, if we take 0.07 and divide by the one that came before, it comes out to 0.1. If I used my sum formula to total these all up, watch what happens. I would get my starting term, which was 0.7, over 1 minus r, which is 0.1. If I did my subtracting, 1 minus 0.1 is 0.9. If I wanted to write this as a fraction, which it wants me to, there's a rule that says, well, if I move the decimal over 1, I have to do it to the bottom. This fraction is 7 over 9. So here's the weird thing. Anytime you have a repeating number, this is weird. So if it would have been 0.5555 forever, as a fraction, that's 5 over 9. You put it over a 9. And why a 9? Well, it's coming from this formula. So that's why 0.3333 repeating is 3 over 9, which simplifies to 1/3. I don't know if you're as excited about this as I am, but I just think this is nuts. Watch this. If it would have been 0.16 repeating, this is so weird. That, since it was two numbers that's repeating, would be over 99. That would be the fraction. If it was three numbers repeating, it would be over 999. This will always work, and it's so weird. But the reason why it works, it's coming from this infinite sum formula. Crazy. So that is the end of Unit 5.